True or false, Euler's method finds exact solutions. False. Euler's method approximates solutions. So we're going to talk about slope fields and Euler's methods today. These are a qualitative and a quantitative technique versus analytic. So we learned an analytic method last class, which is where you find exact solutions using algebra-like skills, right? But this is going to be qualitative and quantitative. So remember that the geometric interpretation of a derivative dy dt is the slope of a tangent line. Remember from Calc 1? Slope of a tangent line to the curve y of t. So the right-hand side of a differential equation, dy dt equals some stuff, gives you the slopes of the tangents, slopes of the tangent lines at various points on the graph of y of t. So we can get a rough idea of the graphs of the various solutions to a differential equation by sketching its slope field. So you select some points in the ty plane, compute dy dt at each of those points, and then you can draw a little mini tangent line. And once you have a lot of those mini tangent lines, the shape of the solution begins to present itself. So I want to sketch a slope field for dy dt equals y minus t. This is a good example to use for a slope field because so far we can't solve that analytically. It's not separable, so we're going to use some other techniques. So basically, this is the ty plane. And we have picked some random points in the ty plane, and we're going to calculate dy dt. We can calculate it because we have a formula, right? Dy dt is y minus t. So you just pick, say, 0, 0, do y minus t, 0 minus 0, you get 0. 1, 0, y minus t would be 0 minus 1, which is negative 1. And then you can draw, at each of these points, you draw a little mini line that has the slope that you just calculated. So at 0, 0, I would put a little line that has a slope of 0, like that. Little mini tangent line. At 1, 0, I put a little mini tangent line that has a slope of negative 1. Something like that. Okay, so then I'm just going to pick some other integer points that I've got showing here. Maybe 1, 1. 1, 1, y minus t gives 0. So I have a flat tangent line at the point 1, 1. 0, 1, y minus t gives you 1. So we've got a slope of 1 right here. Negative 1, 0. 0 minus negative 1 is 1. So negative 1, 0, I put a tangent with a slope of 1. 0, negative 1. Negative 1 minus 0 is negative 1. So I have a slope of negative 1 here. And then negative 1, 1. This point right here. 1 minus negative 1 is 2. So that one's going to be steeper than anything I've drawn so far. And then negative 1, negative 1, which is 0. Flat one here. And 1, negative 1. Negative 1 minus 1 is negative 2. So steep negative line. So that's the idea of how you create a slope field. I think I just heard some mumbles like this is a pain, right? Sketching a slope field by hand is tedious. It's best to have a computer do this. They can do it super fast, populate a whole screen with some mini tangent lines. A computer wouldn't just do it at integers, it would do it at lots of points in between the integers. Your graphing calculator can do this, so can some free software like GeoGebra. I have instructions in a couple minutes. Yeah. So here's a more detailed slope field. So this is the same equation, dy dt equals y minus t. I created this using some computer software. And now you can trace out some particular solutions that correspond to various initial conditions. Okay, so somebody give me an initial condition, y of 0 equals 1. Okay, so if I wanted to sketch the solution to this differential equation that has this initial value, I plot the point 0, 1, because this is t, y, and then you just kind of follow the slope field, right? It's very qualitative. You just kind of follow the mini tangent lines. So this actually looks like it might be a straight line solution. Yeah. Right, and then I've sketched several other solutions that correspond to different initial conditions. So you just follow the slope field. And you can get a pretty decent picture of what your solutions look like. So some technology you can use to create slope fields. I put a link in here. If you open this in Moodle, the link is live, so you won't have to type it all in. But there's a link here that you can download a program for your 83 or 84 to create slope fields. Your 89, it's built in, so if anyone has an 89, there's directions on how to do it. And then in GeoGebra, it's just the command slope field. Right, so in the input bar, you type slope field, and then the right-hand side of the differential equation, and it'll populate a slope field for you. So in general, I'm not going to ask you to create slope fields, whether by using technology. On a quiz or something, I might ask you to do like a couple of integer points like we did in the example, just so I know that you know how it's created. But if you need a slope field, I'll generally give it to you. I'll make it with technology and give it to you. All right, so we're going to move on to talk about slope a little bit more. Okay, so we've been dealing with slope fields. Let's be a little bit more specific and bring in some numbers here. A little bit less qualitative, more quantitative. So if you have a line with a slope of 2 and delta x is 3, what does delta y have to be? 6, yeah, because delta y over delta x has to be, is the slope. That's the definition of slope. So if my slope is 2, delta y I don't know, and delta x is 3, you can just multiply to get the delta y, right? So delta y is 6. So in general, since slope is change in y over change in x, then the change in y you can also always get by doing your slope times your change in x. Just a simple algebraic manipulation there. Change in y is always slope times change in x. All right, Euler's method is a numerical technique that gives us a precise way to draw a particular solution by, quote, following the slope field, right? It just allows us to follow the slope field with a little less like eyeballing it, you know? Gives us some numbers to use. So Euler's method takes advantage of the fact that the tangent line approximates the solution curve near the point of tangency. So you might also remember this from Calc 1, right? If you have a curve and a tangent line at a particular point, when you're close to the point of tangency, the tangent line and the curve are really, really close to each other, right? So we can use the tangent line instead of the curve. So that's the advantage of a differential equation. You know everything about the tangent line, and as long as we're really close to the point of tangency, it can really approximate the curve well. Okay, so do an example here. We've got an initial value problem. dy dt is t minus y squared. Again, this is a good candidate for Euler's method, a numerical technique, because we can't solve that analytically. And our initial value is y of 0 equals 1. Okay, so I've got the slope field created for you. We're going to try to just follow the slope field to sketch the solution to the initial value problem. So if y of 0 is 1, that's my initial condition. And then I'm just going to try to kind of follow the slope field. It looks like it starts out going down, comes back up. Let's see. Maybe, I don't know. It's really hard to follow a slope field. Something like that. Kind of flattens out for a second there. All right, so now this is my curve, y of t. That's my solution, a picture of my solution. I don't have a formula for it, but I could try to use my picture to estimate y of 0.5. So y of 0.5 looks like, I don't know, about 0.8. And y of 2. Mm, 1.3, something like that. So that's all like pretty wishy-washy, right? It's all qualitative. And so I can get an idea of the shape of my graph, but the 0.8 and the 1.3, not very rigorous, right? So I want to estimate y of 0.5 in a better way. So I'm going to draw a picture. I know the slope of my tangent line at 0, 1, or I can calculate it, right? I know that dy dt, the slope of the tangent line, evaluated at the point 0, 1, which is my initial condition, is going to be 0 minus 1 squared, just plugging into the differential equation, and I get negative 1. So I'm going to draw my tangent line with a slope of negative 1 here. A big tangent line. We might not use the whole thing, but big tangent line. Okay, if I want to know y of 0.5, y of 0.5 is what I'm interested in. What is that? I can use the fact that my tangent line is an approximation to my curve as long as I'm near the point of tangency. As long as I'm near 0, you know, if I'm in the general vicinity here, my curve and my tangent line are close together. So let's call 0.5 near 0. It's not really, but just to give you the idea. Okay, 0.5 is pretty near 0. So I could say, well, my slope is always change in y over change in x. And my change in x that I'm interested in is 0.5, because I want to know what y of 0.5 is, and I know what y of 0 is. So my change in x is going to be 0.5. And my slope of my tangent line, I know, is negative 1. What I'd like to know is my change in y. Okay, so my change in y ends up being negative 0.5. So if I were to draw this in my picture here, erase this box. Okay, so I know my change in x was 0.5. Here's my change in x. Here's my change in y. I know the slope of this line. Delta x is 0.5, and I solved for delta y, negative 0.5. So this point right here on the tangent line, this point approximates the point on the curve, right? Because I used 0.5, which is actually pretty far from 0, it's not the best approximation, right? But this is the real y of 0.5. This is what Euler's method predicts y of 0.5 would be. So this says that y of 0.5 is approximately 0.5. So I know my change in y, my new y, y of 0.5, is going to be my original, what y of 0 was, plus the change in y. So y of 0.5, I should say approximately. Y of 0 was 1. My change in y was negative 0.5. So I get 0.5 as my approximation for y of 0. I mean for y of 0.5. So that is Euler's method. And we can continue. I'm going to continue to do this to get y of 1, y of 1.5, and y of 2. I'm just going to keep taking delta x steps. Sorry, I should have said delta t. Those are all delta t's. I'm going to keep stepping by 0.5 along t and get values for the solution function y. All right, so I'm just going to fill in what we already did here. So k is just the step that you're working on. So this is going to be 0, 1, 2, 3, 4 steps we're going to take. Okay, so t, that's your value of t at any given point. So my initial value of t was 0. My initial value of y was 1. 0, 1 was my initial condition. dy dt, which in this case is t minus y squared, came out to negative 1. Delta t, we're using 0.5. And then delta y is always m times delta t. So in this came out to negative 0.5. All right, so then we move to our next step. And we say our next t value is the old t value of 0 plus the change in t. Right, so 0 plus 0.5 is 0.5. And my delta t is always going to be 0.5, so I can just fill this in all the way down. This is what we have control over, how big a step size we take. So this is going to be 1, 1.5, 2 will be my t values. All right, my new y value is your old y value, which was 1, plus your change in y, negative 0.5. So this is old y plus delta y. So 1 plus negative 0.5 is 0.5. So now I have a point on my solution curve, 0.5, 0.5, or at least it's close to my solution curve. So now I calculate the slope at 0.5, 0.5 by plugging into the differential equation t minus y squared, and you get 0.25. 0.5 minus 0.5 squared is 0.25. Delta y is always your slope times your delta t. So 0.25 times 0.5 is 0.125. And then you can fill in your new y value. Your new y value is your old y value plus your delta y. What your y was plus how it changed. So 0.5 plus 0.125 is 0.625. And now I've got another point that's close to my solution curve. It's supposed to be really close to being on the solution, 1, 0.625. Plug into the differential equation, so I just do t minus y squared, 1 minus 0.625 squared, and I get 0.609375. And then your change in y is your slope times your change in t, and that's 0.304687.5. Best not to round at all if you can help it, because your rounding errors could compound as you do more and more steps. Okay, my new y is my old y plus my change in y. So that comes out to 0.9296875. So now I have a point at t comma y, 1.5 comma 0.929. Plug that t and y into the differential equation to get a slope. So t minus y squared, 1.5 minus 0.929 squared comes out to 0.63568. And I might have rounded there, I'm not sure. I don't remember. Probably. I think I did round when I wrote it down, but my number, but I used the whole number, like I had my calculator store that number, which is fine for you to do too if you're ever writing this down. Okay, slope times delta t gives you delta y, and you get 0.3178, and then a bunch of other stuff. That's your change in y. Add that to your old y, and you get 1.25 if I round it to 2 decimal places. At the last step, you can round it. Yeah, you don't want to round along the way because the errors will compound. But what I was looking for was y of 2, right? So that is what I want, 1.25. At this point, you can round it. So that's an approximate value for y of 2, 1.25. And then let's look at our picture again. We approximated y of 2 to be about 1.3 from our drawing. And Euler's method gave us 1.25. Not bad. Yeah, you don't even have to finish out the table because what we were looking for was an approximation for y of 2. Right? When t is 2, what is y? Got it. No need to finish the table. So that is Euler's method. That's how it works. And you are going to start on your activities now.